right, let's go ahead and review some things from our last lesson. We began talking about the most abundant state of matter on our planet, Michael.
Water.
Well, that's not a state of matter. Liquid in general, though granted the most abundant liquid on our planet would be water, yes. We said that liquids in general, not just water, but all liquids, have a tendency to try to get the smallest surface area possible. That is, they tend to resist increasing their surface area. What do we call this resistance to increase surface area, Kendall? Surface tension. We said surface tension is caused largely by two intermolecular forces. That makes it sound cool. What are those two intermolecular forces, Audrey?
You have adhesion and cohesion.
Good, adhesion and cohesion. Which one is the water or liquid molecules sticking to the other substance? Adhesion. Adhesion. And then therefore the liquid molecules caught sticking to each other is cohesion. There we go. So remember, co meaning with, so it's the with or together, the same thing, and then add meaning away from? Anyway, I don't know. Trying to get into those prefixes, root suffixes. Y'all did that class already, so we'll move on. We also said adhesion and cohesion, along with atmospheric pressure, help to explain liquid's tendency, for the most part, to rise in a narrow tube. What is this phenomena called? Kendall? Capillarity. And we did say there's one liquid that will sink instead of rise in a narrow tube. Audrey? Mercury. Because of its density, mercury will sink, and also because mercury has a stronger cohesion than adhesion. Most liquids, it's the other way around, where the adhesion is stronger. We said that as the liquid rises, or in some cases, in one case at least, falls in the narrow tube, there's a curved surface at the top, curved right around the edge of the liquid. We call this, Michael, you knew I was coming to you.
Meniscus.
The meniscus, very good. And by the way, we did indeed pick on his sister about the calculator and said he could conquer the meniscus, she can conquer the calculator. But anyway, for those watching on YouTube, if you have no clue, you have to watch geometry lessons. And starting about lesson 30, because that's going to be the new recordings. Anyway, so you could be famous in multiple classes this year. Yes. Just for a brief time of fame in the geometry class. They get more fame than you. All right. Anyway, we then talked about the study of liquids at rest, and what nice, cool sounding term describes the study of liquids at rest, Audrey?
Cool sounding?
It just sounds like it's smart and impressive. It's just liquids at rest. Kendall, help her. Hydrostatics.
Yeah.
Like, wouldn't that be like the cool title for like a science project? Say, set the STEM fair or something. Hydrostatics. We're not budging. Something, I don't know. You could come with a cool title. We won't budge, But anyway. My dad came up with this verse. We sang in church the other night. I shall not be moved. I shall not be moved. Well, anyway, my dad came up with this rendition for a large friend of his in college. And instead of just like a tree that's planted by the waters, it was just like a hippo in a shallow stream. I shall not be moved. Well, Chloe just loves that version. So I'm watching from the choir as she's down there singing, and I'm reading her lips. And sure enough, she's singing. I'm trying to be, mature and stuff. I'm in the choir. So I'm trying to sing, the right words, which sometimes I get confused which ones are the right words. I've sung it wrong so often. I can see her down there now as she's singing, just like a hippo in a shallow stream. So she catches my eye and she laughs and she tells Mom. But anyway, how do we get off on? Oh yeah, I shall not be moved. Hydrostatics. Okay, anyway. That was random. Hydrostatics, study of liquids at rest. And we said that even at rest, even when the liquid sits there doing nothing, it's doing something, it is pushing. In general, any push or pull, Audrey, is called force. And we said that for a liquid, as it pushes, there's this force on everything it touches. It pushes on. We said that it's going to push perpendicularly, big long word. There's a nice, easier physics word for perpendicularly. Normal. And it's just an easier word, right? Normal force, perpendicular force, exerted on everything the liquid touches. We said force is going to be measured in what unit, Michael? Newtons, very good. And we said that Force is just how much push there is. If we want to account for how much push for a certain amount of area, then we're talking about, Kendall, pressure and your stilettos. And do you actually have stiletto heels? You don't do that?
I mean, I have a few pairs of high heels.
Not that you wear here, obviously, because that'd just be murder, but maybe in more senses than one. Murder to your feet most of the day, and somebody's unkind, makes the wrong joke, you know. I'll be nice to you the rest of the year. Just don't bring the stilettos to school. Anyway, but force per unit area we call pressure, right? We said pressure is going to be measured in what unit class? Pascals. But the definition of pressure, I said a moment ago, pressure is force per unit area. That gives us our first equation for this chapter, Audrey. Our equation for pressure in general is?
P equals F over A.
Good, P equals F over A. And this is essentially your definition of pressure in equation form. And we will occasionally use that equation in this class. However, we kind of transitioned and talked about finding the force that a liquid bears down on the bottom of a container, whether it be the bottom of a drinking glass, the bottom of a swimming pool, whatever. To calculate force at the bottom of a container, what equation do we use? Volunteer. Audrey's like, I think I remember.
F equals rho GH.
Close.
A.
Rho GH, right? The force that comes to bear on the bottom of a container is equal to the cross-sectional area of the bottom times the, what does rho mean, class? Density of the liquid times, what is G? The pull of gravity. Obviously, if it weren't for gravity pulling down on the liquid, it wouldn't be pushing down at all. So really, it's kind of gravity getting it all started. And then the H is the height of the liquid from the bottom. Normally, we think of liquid as having depth. Yeah, H for height, whatever. By the way, if it's pure water, which a lot of times we'll assume, what is the density of pure water, Michael?
1,000 kilograms per cubic meter.
Good, you read well, 1,000 kilograms per cubic meter. And again, we used to use 1 gram per cubic centimeter, but we're going to be dealing with larger quantities now. And since we want force in newtons, which is a kilogram per meter per second squared, we need the kilograms. What about G? Technically, it differs depending on where you are on the Earth, but we're going to use what kind of rough estimate average value for G? Kendall? 9.80 meters per second squared. And of course, this means the area will need to be in square meters and the height in meters as well. Force measured, class, in newtons. Good. We said, of course, the force then has to account for the cross-sectional area of the bottom. Well, what if we just wanted the pressure at any point on the bottom? We wouldn't need the cross-sectional area, right? So if we wanted just pressure, what's that equation? We call this equation the law of liquid pressure, Audrey.
Rho GH.
That's just rho GH, and this is the equation, the law of liquid pressure, which again, same things, just you don't have to account for the area. I want to talk about, next thing in your notes, a few implications of this law. A few things to consider as we look at the law of liquid pressure, rho GH. Here's the deal. The density of different liquids, in general, does not differ that greatly. Mercury's the outlier, right? Mercury much more dense than any other liquid, but your other liquids, there's not a huge disparity in the densities. You're not looking at one liquid being 2 or 3 times as dense as another. They're all in kind of the same ballpark. Some will be a little less than 1,000 kilograms per cubic meter. Some liquids a little more than 1,000 kilograms per cubic meter. But there's not going to be a huge noticeable difference in densities. Gravity will differ depending on where you go on the Earth, but it won't differ by much, which is why we use an estimated value. Really, the big thing that'll greatly vary from problem to problem, class, is the height or the depth of the liquid. And therefore, our first implication of the law of liquid pressure is that pressure depends primarily on depth. Pressure depends primarily on depth. Blaise Pascal demonstrated this. He had a pressure reading device, and you see a little diagram there on page 36. He had different containers that all were the same depth, but would have different volumes of water in them. Now, the openings all had to be the same size, so for his pressure meter to fit on them. And he used the flexible diaphragm there so that way the pressure reader could detect it. But you can tell, obviously, there's 3 containers there. C has much less liquid. A has more liquid. B has the greatest amount of liquid. Yet all 3 containers, despite having different amounts of liquid, different amounts of force, all had the same pressure. And it's because, really, the main thing that liquid pressure depends on is the depth. Does that make sense? Okay, so that's the first implication. Liquid pressure depends on what class?
Depth.
Depth. That is the main factor. Yes, there are the 2 other things, but that is the main factor. The next thing then, if it's true that depth is the primary factor that affects liquid pressure, it doesn't matter in which direction you are. At a constant depth, pressure is the same. So pressure is equal in all directions at a given depth. Pressure is equal in all directions at a given depth. Pressure is equal in all directions at a given depth. And there's the little goofy picture that we won't take time to recreate, though I suppose if you wanted to, you could, of the pipes coming out in all different directions from a reservoir. They're all the same depth. They all shoot up with the same amount of vigor. They all have the same pressure within them. The third implication would be this idea of the flow of a liquid from a high reservoir. For instance, most cities have water towers or water tanks in the case of Columbus. How many noticed that Columbus, right there, it's near, kind of near where Cascade Hills Church is. They've got those 2 massive water tanks up on the hill. I believe that's the highest point in Columbus. They want the water stored high, where places in Phoenix City, for instance, build the water towers high, so that the water is up high and has a pressure coming down. Does that make sense? If you were to build something higher, you would need a pressure booster built in to force the water up higher, because on its own, the water doesn't tend to rise above that height. High-rise apartments, for instance, the greatest pressure, if it weren't for other things they do, would certainly be at the floor, ground level. The higher, have you been to Atlanta and seen those 25, 30-story apartment buildings? I couldn't do it. I don't mind heights as long as I'm secure, but just the thought of, what if a fire happened? I'm toast. Okay, I don't want to think about that. What they actually do for those high-rise buildings is they use pumps to force water up to tanks on the roof, and then the water comes down. Well, as the water's coming down, the first floor below it gets some pressure, and the pressure increases as they go. They actually have to build in regulators, though, because the pressure would be too great. You turn on the faucet, just blast you. So they have pressure regulators on the lower floors to keep the pressure from being too great. But if they didn't have the tanks on the roof, I mean, these high-rises are going above where the water towers would be, right? And that's why even like the mills downtown Columbus, right? Though in some cases, I think I've seen some of the water towers on the roof of the building. And so they just have to get it up high enough that the pressure can come down. There's a cool little demonstration. You could do this at home. I'm lazy, so I haven't done it. But you could do this at home easily enough. Take a 2 or 3 liter bottle of soda. Drink the soda so you're not wasteful. Drill some holes in the side, and you'll notice how the water sprays harder out of the lower holes. Now, interesting, the water actually goes furthest from the middle hole. The lower hole is so close to the bottom already, it doesn't have a lot of room for it to continue dropping. You get a greater drop and therefore greater time in the air, therefore greatest distance from the middle hole. But you get the weakest pressure the higher up it is, stronger pressure the further down you go. Why? Because pressure depends on depth. So a greater depth from the highest height of the water head is what it's called. You're going to get greater pressure. Does that make sense? All right. The final thing then, if pressure depends upon depth, and you have a series of connected containers or a series of connected bodies of water. For instance, this could be lake with river or stream. Water tends to, maybe you've heard this, seek its own level. Water tends to level out with itself. We'll actually be looking at a demonstration of this later on, so I'm going to save it for then, where we'll actually connect 2 devices, 2 containers of water with an overhead container, overhead channel of water. Water will still balance itself out, seek its own level, partly because of atmospheric pressure and partly because water seeks a constant depth, a constant pressure. There's an interesting little demonstration there or sketch there of different shaped devices all connected underneath and filled. As you fill one container with water, they all fill to the same level. They also have a demonstration or a little sketch there at the bottom of page 38, how if you had 2 containers and you removed a stopper from between them, they would level out to the same depth. Okay? And I think that's something we've all observed at one point. In fact, the Egyptians observed this when they were building the pyramids. They would kind of dig a trench of water, and they'd use the level of the water to set a constant height so they could build the base of the pyramids level. But again, all of it, because water pressure, liquid pressure, depends on depth. All right. Which is why you dive deeper, more pressure. All right. Any of you actually like dive, like scuba dive or anything cool like that? I know Rebecca in 8th grade. She and her parents, they dive, and that's kind of cool stuff. So your sister has dived.
Yeah.
Okay, the little one has dived. Okay, that's cool. Yeah, I've never dived. I don't swim particularly well. Like I could save my own life, maybe the life of a kid, but I'm not a particularly great swimmer. But anyway, next thing, lateral force and pressure. Lateral force and pressure. That's supposed to be P. Lateral force and pressure. Lateral, of course, meaning sideways, right? For instance, we said you fill tub with water. There's pressure downward. There's also pressure on the side wall of the tub. Now think about it. Pressure depends on depth. Well, at the very top of the liquid, the depth is 0, right? Right at the top surface. Obviously, there's going to be no pressure whatsoever either above the liquid, but even at the very top, the pressure is going to be 0 because the height is 0. At the very bottom, you have the same pressure as you do downward. And since we said pressure is the same in all directions, at the very bottom on the sidewall, the pressure is at its max. It's the same as the pressure downward. At exactly halfway, the pressure is the half of the max pressure. And then, of course, anywhere in between, it's kind of whatever, right? For this purpose, then, we could say that the average lateral pressure is going to be a half rho GH. In some places, it'll be greater than half. In some places, less than half. But on average, excuse me, I mentioned the lateral. The average lateral pressure is going to be half of the downward pressure. It just averages out that way. Therefore, lateral force, the force on a vertical container, would also be half a rho GH. So you don't really have new formulas to memorize. You just need to know that if you're going sideways instead of down, you stick a half on there. That make sense? So you stick a 1/2 on there. Again, this is referring to average lateral pressure, average lateral force. Again, there will be points at which the force is greater and pressure is greater, points at which the pressure and force are less, but on average, it comes out to the 1/2. And this is useful in calculations. For instance, we're blessed, living in Columbus, to actually be able to visualize what a dam is. Where I grew up, we didn't have, damn, what is a dam? But here, I mean, we've got how many different dams along the Chattahoochee just in our area? I know they blasted one of them to make whitewater. And y'all know whitewater? Mm-hmm. You've done whitewater? You've done whitewater? Not know whitewater? You want to do whitewater. I go back to what I said. I don't swim too good. And so the whitewater, I'm like, that's probably a bad idea for me. But life jacket and all of that is, I know they got the helmets, you don't smash your head on it. I don't know, maybe I'm just not adventurous. That's probably it. Probably just a boring person. I'd rather watch football. But anyway, so we're familiar with the idea of a dam, right? It's a wall that's built to hold the water back. The key is when a dam is built, properly constructed, they're going to have a slanted wall so that the wall gets thicker the further down it goes. Why would that be important? There's more pressure down here, right? Greater pressure here, less pressure here, less pressure here, minimal pressure at the top, right? So because there's greater pressure, we have to have that slanted wall built in. But if we wanted to find the force that is pushing on the wall of the dam, well, there we go. There's our formula. Let's look at the example problem there. Example 3.2 on page 39. Read that for us, if you would, Kendall.
The wall of the dam is exactly vertical with a height of 35.0 meters and a width of 176 meters. What is the total force on the wall if the artificial lake behind it has risen to within 3.00 meters of the top?
All right. Also over in Phoenix City, I don't know if you've been to Lakewood Park over there, and there's, I think your brother might have played some baseball games over there, but there's a lake with some houses on it, and there is a dam holding that back. Then there's kind of like a river, but then there's another dam, and then it finally flows into whatever, I think it's called Holland Creek or whatever. Well, anyway, so we got an artificial lake backed up behind the dam, and so here's your water level. There's 3-meter gap from the top. So the water doesn't go all the way to the top of the dam, so obviously it's not flowing over. The height of the entire dam, it says, is 35 meters. How high is the water then, class?
35 meters. No.
The dam's 35 meters tall, but water's coming within 3 meters of the top. So,
30.
right. So I'm going to kind of zoom in now. We're gonna kind of see the dam from the fish view. Okay. So this is the side of where the dam is. This is the dam in front of us. Here's the water level. Okay. Here's the floor, and we're going to make it a rectangle, even though, let's be honest, probably not a true rectangle. Whatever. So there's 32 meters of water rising. It says the width of the dam, side to side, class, is 176 meters. Okay, so that's a pretty significant size. And the question is, how much force is pushing on the wall of the dam total, collectively? Well, for lateral force, class, we want to use the equation. F equals a half A rho GH. The sublat there just reminds us it's lateral. A half A rho GH. So we'll take a half, or 0.5, and then we need the area. Well, what area is being touched by water? 176 by 32. How much area is there on the wall of that dam, class? 5,632. All right, meters squared of area. All right, the density. Well, again, probably it's not pure water, but it's going to be close enough for the density. Let's just say
1,000
cube. All right. The gravity. Well, again, we don't know where exactly we are on the planet, but we're going to use a nice rough estimate for the gravity, class. And then finally, the height. Well, notice we're going to end up using a number we've already used, haven't we? Because it's lateral, the height also functions as one of our dimensions for the area. Our height here is 32 meters. And it's as easy as multiplying them all together. Obviously, we're going to get a really big number because there's a whole lot of force pushing on this dam. And I'm going to put my calculator in scientific notation because I don't want to write that entire number. So I'm going to do second function and then the 5 key, the SCI, to get scientific notation. Approximately, going with, is it 2 sig figs? 3 sig figs. Go with 3 sig figs. How much force is pushing on the wall of the dam, class?
8.83 E8.
And force measured in newtons. 8.83 E8 newtons. Did we all get that answer?
Yes, but I have to do how much scientific notation I wanted in.
Oh,
So
yeah.
I'm gonna-
Yeah, I just usually say 9 just so I get as many digits as I could ever want. Yours is going to ask you want 0 to 9, I just hit 9. But you don't have to necessarily. I mean, it's basically asking how many decimal places you want to show. All right, that's a whole lot of force, isn't it? I remember watching a movie, I don't know, teenage college years. Anyway, Force 10 from Navarone. It was kind of set in World War II time, and there was this village where there was this band of resistance fighting against the Nazis, and there was this really important bridge that the Nazis had been using to transport troops. Like, if we could knock out the bridge, then we would be able to stop the Nazis from moving their troops, and the Allies could get a victory and liberate us. And the idea was, well, let's blow up the bridge, but the Nazis guarded the bridge really heavily. And they're like, well, that's not going to work. Well, it was in a valley with a little creek running through it. And just up the valley was a dam with a massive river behind it where they regulated the flow through so that way they didn't flood the valley. Like, well, if we could blow the dam, which they're not guarding as heavily, that would allow a rush of water to knock over the bridge, to knock out the Nazi route, so that, so that was kind of the plot of the movie. If I'm ruining the movie for you, sorry. But the idea was all we have to do is create the smallest little crack. And the dam was so massive, there was actually a tunnel that led through the bottom, the base of the dam, connecting passageway. So they managed to, fake ID papers or whatever, they managed to get in there, plant dynamite, and blew it up. Just a little bit. Like, from outside the dam, you wouldn't have heard anything or seen anything. But it created just enough of a crack that billions of newtons, millions of pounds of water pushing on that wall were able to crumble the dam. Sure enough, it knocked it over. Of course, it had to work that way, right? It'd be a lousy movie if it didn't work. But anyway, now you don't want to watch the movie because you've heard how it goes. But anyway, that was kind of my first, oh, that's cool. Yeah, it's true. There'd be enough force back there to knock out those cool physics. Yeah. Anyway, questions on lateral force, lateral pressure. All right, let's work some math problems here. Page 48. Page 48, end of the chapter. And let's take a look at some problems together that use these different formulas. So far we've got 5 formulas, class. Our definition of pressure equation, class. E equals F over A. This is your definition of pressure. Our equation for liquid force at the bottom of the container, class.
F equals A rho G.
These are on the board. F equals A rho GH. Pressure at any point in a liquid.
P equals rho GH.
Force on the side of a container.
Force mile equals 1/2 J rho GH.
Okay, you're just reading off the board, people. Okay, this is easy time. And then average lateral pressure.
P lateral equals 1/2 J G.
There we go. Okay, so just 5 equations to know. And they're all really similar. We just got to know which one's which. All right, read problem number 1, if you would please, there on page 48. Michael?
I'm on board. The bottom of an elevated water tank has an area of 135 meters squared. The pressure on the bottom is 1.52 times 10 to the 4th pascals. What is the total force of the bottom vessel?
All right, so pretty much the way we want to approach problems is what are we given? What numbers do they tell us? What numbers do we need? And then we pick the equation we need for it. So it says there's an area of 135 meters squared. So on your paper, go and jot this down. We got an area of 135 meters squared. What's the next number that they give us, Kendall?
The pressure on the bottom.
The pressure is,
1.52 times 10 to the 4th.
or E4,
Meters squared. Wait.
1.52 E4
Oh, pascal.
pascals, because pressure is going to be in pascals. And it asks us what is the total force. If you will take the time on every math problem this year to list out what do I know, what am I finding, it'll show you what equation you need most of the time. Which equation do I need that relates these 3 variables, Audrey?
P equals F over A.
P equals F over A. And since we're solving for the F, I'm going to rewrite the equation solved for F, Michael, so that it says F equals B times A is correct. So, hey, I don't have to wonder what to do. I know what to do, class.
Multiply.
Just multiply the 2 numbers together. Life could not be easier. Unless you have to take 2 steps to reach your calculator. And you're lazy. All right. Well, what do we get for the force on the bottom of the container? Kendall?
205.2.
Did you remember the E4? 1 point? Oh, let me show you how to enter this on the calculator. I just realized I don't think I've taught you how to enter scientific notation yet. Do you see right above the 7 key? There's an EE. That's E. Okay? So you'll literally 1.52, hit the EE, and then 4. And then times 135 equals. And Kendall, it gives you
2 million.
so your calculator is not in scientific notation mode, is it? Go and put it back in scientific notation mode. Second function, SCI, which is the 5 key. All right, and what do we get?
2.042 E6.
There we go. Now, we're going to round, though, aren't we? Because we're only allowed how many sig figs, class? 3. So, Kendall, we're going to round our answer to
2.05.
2.05.
E6.
And force, class, measured in newtons. Do you see how to let the calculator do the work for you on scientific notation, whether it's getting the answer in scientific notation or entering scientific notation? Michael, I think yours may be a little different. Audrey, you see the EE key, and you've got a times 10 right here, right?
Yeah, I got one right there too, but it gave
Okay, that's actually easier, isn't it? Yeah.
Yeah, but it gave me that, which isn't correct scientific notation.
Oh, okay. What your calculator did was it multiplied. Oh, you did 1.35 instead of 135. That's why. Okay. All right, again, trying to make sure we know how to use the calculators because we'll be doing these kinds of things the rest of the year. So good opportunity here at the very beginning to figure it out. All right, let's take a look at problem number 3 and read that for us, Audrey.
A cylindrical water tank is 2.0 meters in diameter and 3.0 meters tall. Find A, the pressure on the bottom, and B, the total weight of water it contains when full.
All right, so let's start with the numbers we know. First of all, Audrey, we're given the diameter is
2.0 meters.
and we're also given the height is
3.0 meters.
3.0 meters. Now, like, wait a second, diameter? I don't know, diameter isn't in any of our equations, is it? But what is in nearly every formula that might use diameter, class? Area. If it's a cylindrical water tank, what shape is the bottom? How do I find the area of a circle? Pi r squared. I mean, okay, so this goes back to your junior high days. Write this in your notes because you're going to use this all year long. Area of a circle. I should remember that from junior high. I think I've said this before. You're not allowed to forget anything. Yeah, we forgot something. Area of a circle from your junior high math days. A equals, and your 7th grade and 6th grade and 5th grade math. A equals pi r squared, okay? Diameter ain't in there. What else should we remember from junior high? If the diameter is 2 meters, then that means that the radius is 1 meter, okay? Yeah, radius is half a diameter, something else they expect that we would remember from our junior high days. All right, so if area is pi r squared and the radius is 1, then what's the area of this, the bottom of this tank, class? It's pi, right? Pi meters squared is the cross-sectional area of the bottom. So they gave us the diameter, which allows us to get the radius, which allows us to get the area. Make sense? All right, now look at what it's asking for here. It asks for the pressure on the bottom. Well, what's my equation for pressure on the bottom of a container? Class? P equals rho GH. Well, I see the H. They didn't give me a rho. That stinks. But it's a water tank. So let's assume there's water in the tank. We know the density of water. They're not going to give us that number if it's water. Because they assume we remember it's 1,000. They also didn't give us G. But it's 9.8. So it makes sense then that for the pressure, the only number they really give us to use is the height, because what does pressure depend on? Depth, right? We know the other two things. So at your seats, find the pressure on the bottom. You got your density of 1,000, got your G of 9.8, and we've got the height of 3. And if your calculator is still in scientific notation mode, it'll already be ready for you. What is the pressure on the bottom? Michael?
3.0787.
That's not what I have, Kendall. So we should just be hitting 1,000 times 9.8 times 3.
2.9484.
I got 2.94E4, which I think they're only giving us 2 sig figs in this one, aren't they? Yeah, so we're going to round that off to anyone. 2.9E4. Because again, 4 doesn't bump. Oh, is that why you said 3?
No.
No, that's not why.
Multiplied it by pi instead of 3.
Oh, okay, you put the area instead of the height right here. Okay, that makes sense. Which would be that slight difference, which would give you a 3.0E4. And pressure measure class in? Pascals, careful, pressure in pascals. All right, but then it does ask next, find the weight of the water it contains. Well, I said the weight of the water, class, is the force. That's what pushes down, is the weight. So when it says find the weight on the bottom, it's asking for the force on the bottom. Well, what's my equation for force on the bottom, class?
F equals A Rho GH.
F equals A rho GH. Well, if I have the rho GH correct, I've already got it on the calculator. All I'm missing is the area, which we said is pi, so I can just take what's on the calculator times pi. Instead of re-entering everything, what do I get now for the force brought to bear on the bottom? Back to Michael for redemption.
9.236
E4 again. So we'll round that off to, again, the 2 sig figs.
9.2.
And force measured in. Questions on that? Questions on problem number 3? All right, and let's take a look at one more and then I'll let you go for pizza day. Problem number 5, read that if you would. Let's see. Michael, I think we're to you.
Okay. A hemispherical bowl 4.40 centimeters in diameter is filled with a liquid of density 805 kilograms per cubic meter. Find the maximum pressure exerted on the interior surface of the bowl.
All right, so this is probably some kind of oil which has a lower density, right? Water's 1,000. This is something that's got a density of only 805. So a lower density here. And it's looking for maximum pressure on the interior surface of the bowl. Now it says hemispherical. What does that mean? Half a sphere, right? Of course, we've got the cross section here, right? So kind of something like that, a hemispherical bowl. Now most bowls actually have a flat portion on the bottom. Not this bowl, because that would mess with the math and we're lazy. So we're just going to assume it's a perfect hemisphere. Question, it says find the maximum pressure. Where would the pressure be maximum? At the very bottom, correct? At the absolute very bottom. So that's the pressure we're looking for. How do we find pressure at the bottom? E equals rho GH. Now the density they give me, class, that's the...
1,000. No.
It's not water this time.
Oh.
They actually gave me the density. 805 kilograms per cubic meter. The G we assume, class, to be the 9.80 meters per second squared. The question is the height. It doesn't tell me how tall the bowl is. But what do they tell me?
They tell you the diameter.
The diameter of the bowl is 40 centimeters. And it's a hemispherical bowl. So,
Yeah.
well, I don't need an area, right? Pi r squared would be area. I don't need an area here. I just need to know from the dead center of the bowl down to the bottom point. How deep is it? Good, it's going to be 20, isn't it? Because in a sphere, from the center point, the radius is the same literally everywhere. So if it's 40 in diameter, the radius is the height. The radius here is 20 wait a second, centimeters? Notice here I've got meters. Here I have centimeters. Can I mix those? So I'm going to have to change this. How many meters is 20 centimeters? We're going from an E -2 to an E 0 because it's the unit. So the E is going up 2, she up and left 2. So Michael's right. We're going to move it 2 places to get 0.2 meters. And so we just multiply those 3 numbers on the calculator. Your 805 density, your 9.8 gravity, and the 0.2 height. And what is the pressure at the bottom of this hemispherical bowl of what I presume to be some kind of cooking oil?
1.57.
E3. We'll round it off. Is it 2 sig figs again? Oh, it is 3 sig figs. Okay, so it is important that the next digit was a 7. All right, so 1.58 E3 and pressure measured in pascals. All right, questions on that? You're going to have a few problems like these for homework this evening. So for homework, I need you to read over pages 39 to 43. Read over pages 39 to 43. On page 48, answer questions 20 through 22. On page 48, answer questions 20 through 22. And do problems 2, 4, and 6. Page 48, questions 20 through 22, and problems 2, 4, and 6. We'll take a look at all of that in our next lesson. Have a wonderful rest of your day, and you are dismissed.